Cool. Hi, everyone. Thanks for inviting me. My name's Charlie. I'm on the Google Chrome team. I work mostly on the Privacy Sandbox APIs, which use a lot of differential privacy. So over the last couple of years, I've become pretty familiar with the concepts. So I thought I would just give a quick intro for you guys. We don't have like a ton of time, so I'm not gonna give a whole motivation for how differential privacy came to be, sort of the de facto notion of privacy in the academic literature. But there is a very rich history of past privacy definitions that sort of fell flat. So if folks are interested in that kind of history, let me know and I can share some references. But I'm gonna just dive right into it because we don't have a ton of time. I'll start by basically giving some intuition behind DP. We can sort of think about differential privacy as operating on a data set. So a group of people that are submitting their data. The data, this is sort of the raw data, and it kind of goes through some magic black box, and you output some more data. So this is kind of the DP magic happens here. And the guarantee that differential privacy is going to give you is that after going through the magic, you won't really be able to distinguish two outputs if they came from inputs that differed on one individual. So the intuition here is that's kind of whether you contributed or not, or whether you participated in the system or not, is not really going to change the end result in some formal mathematical way. And so this should make you feel comfortable because your data is really not going to really be you're not really going to be able to be identified whether you participated, assuming the parameters that you choose here are strong enough. And this is, we would hope that this is enough to show that the system is private because your data did not really impact the end result. So I know we're also talking, I looked a little bit over this proposal for bimodal navigation and metrics, and it seems like local differential privacy is something that you guys are considering. And so I just wanted to kind of mention what this picture looks like under local differential privacy. Here we kind of assume the data set is just one user or one example or one row, in which case what you want your guarantee to be is basically it's kind of whatever is your input, the data looks the same. And you might think this would lead to useless mechanisms, which you might actually be the case depending on the use cases. But it turns out that sometimes if you can post-process this data in aggregate, you can sometimes recover pretty decent aggregate results, even if looking at the result from one row through the magic box actually is almost they're indistinguishable from each other, and there's almost no signal that's coming out of this black box. So this is the high level intuition. We want the input to not really change. What's the formal definition? How do we actually show this formally in a mathematical sense? And here's kind of the formal definition of differential privacy. We have some randomized algorithm N, which is the magic, M for magic. And it satisfies epsilon differential privacy, which is kind of a parameter to the system. If for all pairs of neighboring data sets D and D prime, these kind of are two examples where you remove a person or you change your input. And for all possible outputs of the mechanism, we show that the probability of the mechanism producing that output is close to this e to the epsilon parameter. And so you can kind of see this on the bottom graphic. You kind of have the mechanism induces a probability distribution because these mechanisms are typically randomized. And you want to look at the distribution like, under one data set and then like a neighboring data set, which is like, oh, with someone's data removed, with anyone's data removed, with anyone's data added, or like potentially like you can look at like modifying data, these kinds of things. And we're going to like look at every single point in this distribution and like show that they're close in this like multiplicative sense. So yeah, we have like the blue line is less than or equal to like e to the epsilon times the red line, and like vice versa. So this is kind of like a distance metric on probability distributions. So a few important pieces here. We have this like epsilon parameter. This is like a measure of privacy loss. So when you see higher epsilons, you should be thinking like higher loss, higher privacy loss. When you see lower epsilons, you should be thinking lower privacy loss. And we'll go over like sort of a semantic interpretation of what this epsilon means in a few slides. And like when we're talking about neighboring data sets, this is another really important thing when we're designing like a privacy mechanism. This is kind of like the scope of what you're trying to protect. So when we're thinking about something like a new noisy feature that's on like performance navigation timing, like, you could be saying, oh, I want to like make sure that any one like navigation is protected. Or I could be thinking like more broadly and say, oh, I also want to protect like all of the user's navigations, maybe over a certain time window or something like that. So this is like both of these parameters to the like DP definition are like very important for you to kind of like think through when you're designing a DP mechanism. And so yeah, this again, the neighboring data set thing is kind of looking at like what we're considering when we're looking at like these data sets that are next to each other that we want to have this relation hold for. So yeah, it's a lot of math, but we'll actually it's not too bad. And there will be, I'll go over like 2 mechanisms in the slides with proofs, and the proofs are only like, a few lines long. So yeah, let's talk about this. How do we interpret epsilon? Because I think this is like a very difficult problem. Because like, let's say I have a DP mechanism and I say, oh, I shipped it and its epsilon is 10, or I shipped it and its epsilon is 0.1. Like, how do you know like how protected your users are with these different parameters? I would say this is almost like a little bit of an open question in the literature. Like, epsilon is like notorious for being like hard to interpret. This is the best kind of interpretation that I have found, which is to look at this in sort of like a Bayesian sense of like, hey, we have like some adversary, and the adversary has like a prior probability on like whether you did the like sensitive thing. Maybe your sensitive thing is whether your system is in a high entropy or a low entropy state. Maybe your sensitive thing is like whether you have a particular disease or not, something like that. So your adversary has some sort of prior, and before they look at the data, and then they look at the output of your like privacy mechanism, and you're looking at like how the prior has updated. So you can kind of think intuitively that if your prior updates quite a lot, then you've like revealed a lot of information about that sensitive bit about the user sensitive data. And so you can think about epsilon differential privacy as like bounding the prior update, kind of. And so we can actually look at various values of epsilon and see like how they update a certain prior. And that's like what this like graphic is showing us. Like on the x-axis is kind of your like initial suspicion, like this is your prior, and the y-axis is kind of like how that prior can get updated after they look at the data. And so like either, you'll be updated higher because, the data said that you did the sensitive thing, or lower if they said you didn't do the thing. And like the most private mechanisms will, not update too far. So you can kind of look when epsilon is low, this is like the purple kind of like cold color regime. You're not straying too far from this like diagonal line. whereas like higher epsilons, you're straying quite far. So like, yeah, and there are a few kind of like sort of simple values of epsilon, like if epsilon is 1.1, you know, if your adversary was like 50-50, whether you did the thing, it will be updated to like 25% or 75%. You know, whether you have cancer or whether your system is in high entropy state, whatever. And so you might be able to like kind of stare at a chart like this, like consider an adversary that you're trying to like protect against, and think about kind of what priors they have on this like sort of sensitive data from any user, and think about like our comfort that it would be updated to, you know, whatever this chart says it would be updated to. Yes, Michael, higher epsilon is less private. That's kind of here. Higher is more privacy loss, higher epsilon. So yes, exactly. And basically epsilon, as epsilon goes towards 0, basically what you're saying is that the like probability of any output is like equal no matter what the input is. And so you can think of it as like the signal being completely removed from the entire system when you set epsilon equals to 0. So that's like at least at like one extreme of like the most private is like you're not revealing anything about the input. In which case, yeah, you would be exactly along this diagonal line. Like your prior is not being updated at all. So yeah, here's semantic interpretation. I found it a little bit useful. It's still, I would not say it's like, you know, a silver bullet. It's still really hard to understand, but hopefully this helps a little bit. Okay, I'll go over a few kind of useful properties of differential privacy. These properties are not obeyed by a lot of other like weaker privacy definitions, and these are one of the reasons like that DP has become so popular. So one is that like DP is like composable. So if you have two differentially private, like epsilon differentially private mechanisms, and you kind of like invoke them both over the same data set, then your epsilons like sum up. So if you know, if you have, if you're trying to protect a, you know, a navigation performance, and you have, you know, noisy bimodal system entropy thing, and then you wanted to introduce like another noisy bit afterwards, you know, you can just like sum up the epsilons, and you know the like the privacy loss of the like combined mechanisms, and you can kind of keep doing this arbitrarily. We also know that differential privacy is closed under post-processing. What that means is that like staring at the output of a DP mechanism and like applying random functions to it will like not cause like more privacy loss. So that's like f of m of d is like going to be epsilon private epsilon DP for any function. This is like not the case for all other privacy definitions. So this is like a useful property. We can kind of like, you can go hog wild on the output of this thing and you'll be fine. The users will be fine. Another kind of interesting property is called group privacy. So if you want to protect more than just one user, and you want to protect like a whole group of users, you can use differential privacy for that as well. And the way to think about that is like in the graphic here, you know, you're like adding or removing like a whole group, like of k people maybe. So you want to say like any k people, I want to like I want to protect and make sure that their input is not overly affecting the output. So DP can do that for you, and you basically blow up your epsilon by a factor of k. So these are all pretty useful. The next thing I want to go over is a few examples of privacy mechanisms that satisfy differential privacy. So this first one I think is like very relevant to this system entropy proposal, because it's like, you know, if you're talking about like, oh, we want to like noise a bit, randomized response is like the classic algorithm. And here's the algorithm on the left. We take in a data set, which is just a single Boolean because we're like in the local DP regime. And we take an epsilon value. You compute this flip probability, that is that's based on the epsilon parameter, and with probability that's like proportional to p, you just pick a random, you just output a random bit. Otherwise, you output the data truthfully. And so here's like what the probability distribution looks like if you call randomized response with like the value true and your epsilon is log of 3. You're going to be giving the truthful answer like 75% of the time and a false answer 25% of the time. And you'll note that this like exactly matches this this case. 1.1 is like log 3. So here's the proof. I'm not going to go over the proof, but you can read it if you want to. But it's pretty simple. Another privacy mechanism that's like very common in the literature is the Laplace mechanism. The Laplace mechanism basically just invokes the Laplace distribution, which is this like two-tailed exponential distribution, whose formula is right here on the lower right. This is not necessarily like a local DP mechanism. So the data set here, we're going to say takes in a sequence of like Booleans. I just say Boolean here to constrain the input to be like every user is either submitting like a 0 or a 1. So our neighboring relation will be like, you know, you're adding or removing one user. We're just going to sum up the Booleans, which will give us like the sum of users who are submitting true. And we're just going to invoke this Laplace mechanism centered around the true value, but we're going to scale it based on epsilon. So this gives you this probability distribution that's like centered around the true value. Here the true value is 30, and our epsilon is again log 3. And you can kind of see that, you know, most of the time you're going to get around 30. Here's the proof. I'm not going to go over it. So now I just want to spend the last couple of minutes talking about like how it relates to the system entropy proposal, which I read up on. Yo gave me the link. Hopefully I'm not making any mistakes. I think I understand the proposal. The first thing is just like more general considerations for like when we're thinking about adding differential privacy to something. One really important thing, again, I think I mentioned it earlier, is like consider what is your neighboring relation, like your D and your D prime data sets. This is kind of the scope of what you're trying to protect. Are we trying to protect the system entropy associated with a particular navigation? Are we trying to protect the system entropy associated with like lots of users navigations? You know, like if we want to look at some like aggregate for any one particular user, these would describe like very different kinds of protections that you would want differential privacy to give you. The other thing is like DP like will add noise to the data. Like we looked at a few mechanisms that add noise. You really need to make sure that the noise is like going to be okay. Like we don't want to ship something that is like so noisy no one uses it. This just like adds complexity to the web platform. And that's just bad. So we want to do like a lot of research. We want to do like a lot of vetting that this thing, if we add the noise to the privacy parameters that we want, we're going to like be like shipping something useful. And lastly, I think, yeah, think about what privacy mechanisms are available. I outlined kind of like two general techniques. Like one is like the local mechanism, which is like noising one user's data, and one is kind of like a more central mechanism, which like looks at adding noise to like an aggregate or something like that. That's like the Laplace mechanism. I think that you guys are looking at this like local regime, but like one thing that gives you is like a lot of flexibility if you want to do like event level data splits using a noisy system entropy bit. But like if you kind of know what aggregates you would want to like query, you may be able to get less overall noise. You kind of have like O of 1 noise versus like O of square root of n, where n is the number of records for a local DP mechanism. And there's like, I've linked a few like sort of like prior art in the kind of like central trusted aggregator setting if you want some trusted entity to be doing your like aggregation and noise addition. And then this is my last slide, but hopefully people can see this. But I just wanted to kind of give an example of how you could use like something like randomized response to do like a data split for like performance timing histograms. Because it's like a little bit subtle. If you think about, especially if you think about these, this system entropy as like inducing like a bimodal distribution, you can kind of see on the right, this is like the raw data of like, I just generated some like random Gaussian, sampled from like a random Gaussian distribution for like the low entropy samples, and like also maybe from something like with higher latency for the high entropy signals. But like if you just kind of like naively applied like randomized response on these histograms, you would kind of get something that's like super scrambled and biased. And so here you can see like, oh, we're actually, if we just like randomly looked at every, randomly flipped every input and put it in like the low entropy or high entropy histogram, it's gonna be all kind of like mixed together. So you see like a lot of the mass from the low entropy bucket kind of like moved to the high entropy bucket. And now it looks like the high entropy is actually like a lot more performant than the like real answer would be. But there are techniques to kind of like debias the data and kind of get corrected counts. And so I've given like the formula here and like a link to a proof. But here's kind of like what this would look like after you like compute the per bucket unbiased estimator. And you can kind of see that the like third graph is like pretty similar to the first one. There's like a few negatives here and there, which are like probably kind of weird and like might mess up your measurement systems. But like overall, it's like not like terrible. And if you had like fewer samples, here I had 10,000 samples from the low entropy distribution and 3,000 samples from the high entropy distribution. If you have fewer samples, you would notice that things would get a lot more noisy. But yeah, make sure you do something like this if you're looking to analyze like the impact of randomized response, something like randomized response. Okay, yeah, that's all I have. Hopefully this was useful. I don't know, Yo, if you wanted to wait until the end of the next session for questions, or should we do questions now?